All right, guys. So we have chapter 5, which is Introduction to Newton Laws of Motion. So, in terms of chapter goal, to establish a connection between force and motion. That means in the previous 4 chapters, we've been talking about how the object is moving, what makes object, change position, where that's velocity. What makes object change velocity? Well, that's acceleration. So basically we're talking about, let's say, how the object is moving from point A to point B and how it's basically speeding up or slowing down. And we were saying, okay, so there's acceleration, which makes it slow down to speed up and all of those things. But we never really talked about why is there an acceleration in the first place? What makes a system to speed up or to slow down? So that's kind of what we're going to be talking about in this chapter, because we're going to see, right, there's a, direct connection to, this concept of force and the concept of motion. All right, so first, let's kind of identify what we mean by, let's say, by force. What is a force? Well, technically, any type of push or pull. So basic definition of force is some kind of push or pull. Generally, you have an object that you have to identify, and then basically all the push and pull is happening to the object of interest. And whoever does that pushing or pulling is then known as an agent, okay, known as an agent. But what we have here is, you can see, right, so force acts on an object. So pushes and pulls are applied to something, and from object's perspective, it has a force exerted on it. That means generally what you're going to see here is when we talk about Newton's 3 laws of motion, first 2 laws are technically talks about what happens to an object when you have, multiple forces acting on it. So who does this pushing or pulling? Well, anybody or anything that exerts force, we can call that an agent. Okay, so force requires an agent, something that acts or exerts power. So you throw a ball, your hand is the agent. Gravity acting on the object, gravity is the agent. So table, basically you have an object on the table. Well, the table here can be an agent because it exerts, a force on any object. So technically then what we have here is we have an agent that exerts force on the object. And agent is, could be a person, could be an object, could be anything, right? It could be like, let's say we're going to see there are 2 types of technically agents. One type that exerts direct contact physical force. The other one then can have a force acting at a long range. So we'll talk about that. In any case, so force is a vector, which means we have a magnitude, we have a direction, just like any other vectors. So force to the right is different from force to the left. And any 2 forces that to the right and same magnitude, you can say they are equivalent to one another. But in any case, whatever we learned in the previous chapters about forces, about vectors, sorry, can be applied to forces. That means if you have more than one force acting on the object, then you have to do vector addition of forces. Well, it's basically the same thing as we've been doing before in terms of adding vectors A and B together. Well, here we're doing vector F1 and F2 added together. So in a way, a lot of those things we learned going to be coming back. All right, so as I mentioned, 2 types of forces: a contact force. There are forces that act on the object by touching it at a point of contact. So here's an example, right? A bat, hitting the ball. And there are long range forces, the, type of forces that you don't really see any type of, pushing or pulling directly, but you see the effect. And obviously gravity is the perfect example of that. And in this physics, 220 class, we will be considering only gravity as that type of long range force. In 221, you will then study also electric force and magnetic force. Those are also examples of a long range force. All right, so let's see. Force is a vector. That means if you have an object, then technically again can be represented as a particle, because we are adding a new layer, new variable that we're going to be, let's say, taking into account, which is the mass. But other than that, particles still can be considered, object still can be considered as a particle. That means it's size or shape is still unimportant, so we can treat any object. So let's say it's a box, or it's a car, right? Or I don't know, like let's say a person walking around, right? So all of them can be represented as a particle, okay? So then I can say, all right, so there's a particle, there's a force acting on it in this direction. So then the length of this represents the magnitude of the force, and then you have the direction, okay? General notation for the force is a capital F. So F for the force, and sometimes you can just use F and put some kind of subscript to identify what type of specific force it's acting. And but you'll see there are number of ways we can actually represent specific forces. So, but generally, let's say any type of push or pull or applied force given with capital F. So these are one of the things we do in this chapter is mostly like introduction to forces. What is a force? Newton's laws of motion, how to represent a force, how to draw a force diagrams and things like that. But we have to wait until chapters 6 and 7 to really get into this applications of forces. So we're going to take this as an introductory chapter, and then we'll tackle like really difficult and hard problems in the next couple of chapters. So here's again, we have an example. We have a box and being pulled to the right by a rope. All right, so again, what we have here is a box is our object, and then technically the rope is the agent, even though the person is pulling, right? But the rope is who directly exerts force on the box. So box can be represented as a particle, and then the force acting on it will be to the right in the direction of the rope. We're going to see that we're going to actually call this a tension force. So this is going to be known as a tension force, and it is acting in the direction where the where the rope is, always in the direction. All right. So here's then an example of a different type of force we're going to be looking at later on, which is the spring force. So a box is pushed to the right by a spring. That means now his spring is the agent. Still, box as a particle has a force acting on it to the right because the spring is pushing it to the right. So that force has to be, drawn in, in the direction where the force is acting, which is to the right. So here's the example of the long range force, gravity. Object falling down. Well, previously we said, okay, it's a free fall. So there's a, it's falling down because of gravity acting on it. Well, that's because gravity is a force. So the gravitational force when acting on the object, it basically pulling it down. So that's why the box, and then force of gravity, right? A long range force, it's acting and Earth is the agent. All right, so as I mentioned, the force being a vector have to be treated as a vector. That means if you have an object where the object has multiple forces acting on it, well, you have to add them as vectors, because in order to to find out the net effect, you need to calculate F net, right? So F net is basically you take the object, here's a particle, right? And you see that, okay, so there are two forces acting on it. One, F1, so basically you can write in the direction of that rope one. Another one is F2. So that means, you have F1 and F2. Those are the direct forces acting on the object. All right, so what is then the net effect? Well, the net effect is then the vector sum of those two forces, which is in this case F1 plus F2. But if you have more, let's say maybe like F3, F4, F5, F6, whatever, right? So it's vector sum of all the forces, okay? Which means you are looking for what we call superposition of forces, okay? The net effect. And you can see from here, let's say this is just two vectors. And what you did here, we constructed parallelogram, and we found that F net here is nothing but, the resultant of those two vectors. That means vector sum of F1 and F2 is F net, which we basically, previously we would have called as A and B, and then find the resultant. So technically it's the same thing as saying resultant is equals to vector A plus vector B. We're just now replacing resultant with the F net, A with F1, B with F2, and then just adding them as vectors. That means this box, but after being pushed or pulled by those two forces, will technically have a net effect in this direction. That means those two together combined give a net effect in that direction. And then we're going to see later on, right? So basically, force is what technically causes acceleration in the system. That means the system then will be accelerating in this direction of F net. All right. So we're going to look at some of those specific type of forces, like gravity, like normal force, and things like that. And our goal will be then for the next basically a few slides to identify and learn how to label them in such a way that anybody who looks at your diagram can understand what type of force, let's say, we're talking about. So first is the gravitational force. And the reason that we're first looking at the gravitational force, because that's the most obvious one, and that's the one that's always acting on the object. Gravitational force is one force that no matter what the object is doing, at rest or moving to the right, moving to the left, throwing upward, dropping down, downward, or whatever it is doing, the gravity is one force always acting. Okay. So generally we can put like F of G for the gravitational force, right? So, but sometimes you might see that, if I have F of G, right? Sometimes I might put this as W, because gravitational force is also equivalent to the, to the weight. So that's what we call weight of the object. So that means, gravitational force can also be W in terms of the weight of the object. But in any case, so what we have here is, so right now let's look at this in terms of F of G. So the agent is the Earth, right? And gravity acting on all objects, whether moving or at rest. And the gravitational force has a very specific direction, which is always towards Earth. That means straight down. All right, so that means this is one type of force that we can always consider. The next one we will see quite a lot is a spring force. And the spring force is a little bit different from the gravitational force. Gravitational force is generally can be considered as a constant force. Spring force is not a constant force. Spring force is whenever you take a spring, something like this, you have the object, the box is actually attached to the spring. So when you pull it to the right, basically when you apply force to the right, that means you're stretching the spring, or whenever you're compressing the spring, then the spring actually exerts force on the object in such way that it always tries to push the system back toward, unstretched, or equilibrium state. Okay. That means this is what we call a restoring force. It always tries to restore the system into its original shape. So when you change the shape, stretch or compress, this force is going to try to restore it back to its original shape. So that's why the spring force is known as a restoring force. And generally it is, a force that usually, like, let's say, related to any type of object that has some kind of elastic property. Spring has a very good elastic property, right? It can be compressed or stretched. So, but so can, other things that, have a little bit of elasticity, right? So, so for example, plastic ruler, right? You can, let's say, change its shape a little bit, but things like that. You take a plastic ruler, you bend it a little bit, you let go, so it goes back to its original shape, okay? Obviously, you don't want to, let's say, pull it down so much so it breaks, but let's say if you don't break it, it can always go back to its original shape, unless you deform it, let's say. That's also something that we will not be considering technically. But in any case, F with a subscript SP will be then for the spring force. All right, so the next here is the tension, which I already mentioned, is that if you have a force by, by a rope or a string or a cable or a chain, right? Then that is known as a tension force, okay? So the tension force is always in the direction of the string or a rope or a cable. And you can see, right, so here's a rope, so that's the direction of the tension force, given as capital T, okay? So one of the things we're gonna talk about here is, you can see, right, so the rope is made of atoms joined together by molecular bonds. So molecular bonds can be modeled as a tiny springs holding the atoms together. So tension is a result of many molecular springs stretched over so slightly. Okay, but a lot of times we're going to see that we can actually ignore that, little bit of elasticity property, and we can assume that the tension in the rope the same basically everywhere. The next one here is a surface. So the surface exerts two types of forces. One type of force is known as a normal force. Normal force is always perpendicular to the surface. So let's say here's your a textbook sitting on the table. So there's going to be normal force acting such that it's perpendicular to the surface in upward direction. So technically that's the force that prevents object from falling down. So let's say your object will fall down because of gravity if there was not a table. Right, so that means the normal force always perpendicular to the surface. So if the surface is flat surface, basically flat horizontal surface, normal force is in a positive y direction. Okay. So, but obviously if we're going to have a surface that changes, let's say there's an incline or something like that, then the direction of normal force will also change, like, I have in this example. So for example, if your surface here, right, like a wall, then the wall technically then exerts force perpendicular to its surface, which will be then horizontal force. And if you have an incline, right, then the normal force is not straight up, but at an angle, right? So that means, don't ever think like normal force is always straight up. It's not. It's always perpendicular to the surface, okay? And it's always a force that's acting on the object, due to some kind of physical contact with the surface. As soon as you're not touching the surface, there is no normal force. The surface also gives you another force, which is parallel to the surface rather than perpendicular to the surface. So this is known as friction, okay? So we're gonna see that there are two types of friction forces. One is a kinetic friction, like you see in this, in this slide. And then the kinetic friction is basically, think like this: the surface acting on the object to prevent the motion. That means the surface, in this case, when there is a kinetic friction, we assume that there is a moving object and the surface is acting on such a way to prevent its motion. So that's why, for example, any object rolling on the surface or sliding on the surface, if there is a friction, it will eventually slow down and stop. What makes it slow down and stop? Kinetic friction. Because kinetic friction is opposing to the motion force, and it's always going to be parallel to the surface and always in the opposite direction of the motion. See here, the child is basically moving to the right, friction is to the left. If the child was moving to the left, friction would have been then to the right. So it always opposes the motion. Right, that means surface gives me a normal force and a friction force. So technically those are the component of what I call a surface force. We don't really talk about the surface force by itself, and we always, in a way, talk about its components: perpendicular component and parallel component to the surface. That means, we just ignore this and we just say, all right, so, instead of that, I'm going to just talk about, parallel friction or perpendicular normal force. But there's also a static friction. So the difference between kinetic friction and static friction is kinetic friction is opposing a motion of the object. That means that there is a motion, object is moving, and it's, basically trying to slow it down. The static friction is when object is at rest. That means, for example, right now, if there was no friction, then there will be a gravity acting on the frog, and then the gravity will have a component parallel to the surface and perpendicular to the surface, right? And then this parallel to the surface component would have then have the frog slide down. But frog is basically just sitting there. That's because there's a friction between the frog's, let's say feet and let's say the surface, and the friction is in the opposite direction, which then cancels the gravitational force effect. That means in the x direction or along the surface, right? Both of them cancel each other and object is at rest. That means the friction, static friction, is what prevents objects from, moving in the first place. So for example, try to find something really heavy around you, like a table or something or a desk, and just give it a little push. So if you give it a little push and it's not moving, that's because of the friction. Because if there was no friction, doesn't matter how light the push was, it would have been then, let's say moving forward, your object, the table or desk. All right, so we will be coming back to this type of, as kinetic and static friction forces later on in chapter 6 and 7. But here, think like this. So those two forces, By the way, there's a subscript. We're represented with the lowercase f, and S is the subscript for the static friction, and K is the subscript for the kinetic friction. Okay. Also, the name kinetic means motion, so kinetic friction is friction acting on a moving object. Static means something at rest, so then static friction means, object is at rest. When the friction is acting, that means the friction prevents object from moving altogether. There is also a drag force, which is basically air resistance. So then air resistance basically acting whenever object is falling down, let's say gravity acting on its object falling down, but then, air resistance, right, or the drag force prevents it from, falling at the free fall. That's why the leaves don't fall down like a rock does, right? So, or the piece of paper, right? The leaves are slowly kind of going down. That's because gravity is pulling it down, but then the drag force, air resistance, acting in the opposite direction. So the net effect is still falling down, but maybe at much lower rate. So every time we did free fall, one-dimensional or two-dimensional, remember, we assume that drag force or the air resistance is zero or negligible. But obviously you can see, right, it's a force that's always acting. And if your object is not as heavy, compact object, then the drag force is technically not negligible. Okay, so and then the projectile problems, when you actually include the air resistance, would give you slightly different acceleration, slightly different optimal angle, right, which was 45 for the free fall, right? So it will change things if you take this into account, which again we will see later on. So like, let's say what equation allow us to see how drag force affects the object motion. But here just introducing that, for example, the air resistance, right, is known as a drag force, and we represent it with a capital D. We also have a thrust force. So this is generally from the engines. So let's say anything that has an engine or anything that can be propelled forward, right, is known as a thrust force. So the cars, rockets, or you can actually, propel yourself forward, right? When you're walking, you're basically pushing the ground pushes you, and you actually thrust yourself forward, okay? So, but in this particular case, which we're gonna see later on, is actually a very good example of a Newton's third law of motion. Is the rocket is basically pushing all the gases that it has down, and then the gases then pushing the rocket upward, giving it a thrust in an upward direction. All right, so I mentioned that electricity and magnetism are other long-range forces. We will not be considering them, but those are the other type of forces that we will be learning in Physics 221, not in in this class. All right, so kind of summarize what we learned. So there are general force F, then gravitational force, spring force, tension, normal force, static friction, kinetic friction, drag force, thrust. And you can see, right, each one has a very unique notation. So that's why when we are doing the diagram of the forces acting on the object, then we can try to look for, labeling them such a way that it's easy for you to read and for someone else to see. Like, let's say on the exam, when I'm looking at your diagram, I can understand which force are you talking about, which direction, and so on and so forth. That means by labeling them using this notation makes diagrams much easier to read and much cleaner and easier for me to grade later on. So make sure that you learn about these notations and basically use them on your diagrams. All right, so as I mentioned, what we're doing here is we're identifying the object of interest when we're looking at the forces acting on the object. So what is the object, right? So for example, all right, so you have a box, and then there's a person pushing the box. Which one is the object? Well, obviously the box in this case. So technically it could have been a person too, because there's also forces acting on the person. But in this case, I have a box, and I want to know what are the forces acting on the box. Then I can take the box to be the object that I can represent as a particle at the center, and I can draw all the vectors acting on it. And there are some forces acting on it. So there's a person pushing you to the right. So general notation F. It's on the surface. So there's a normal force upward. And it has a mass, so then the gravity acting on it downwards. So you can see, right, there are three forces acting on the box being pushed to the right. Maybe there's also friction. So then this would have been the friction force to the right. Now, is it kinetic or static? Well, it depends. Is the object moving or is it still at rest? So let's say if it's still at rest, then it's a static. If it's moving, then it's kinetic. All right, so make sure you guys read this, tactics to kind of, understand how to do this. By the way, this diagram is known as a free body diagram. We're going to talk about that. So free body diagram. And it's the best tool to use to start solving physics problems, involving forces. So just like vectors, remember? So you need to do the diagram to sort of like estimate what's going on. Here, whenever you're dealing with forces, this free body diagram allows you to identify your object, put in a coordinate system, draw all the forces, and visually see, so like, let's say, what's going on to the object. All right, now let's talk about, what do forces do to the object? All right, so think like this. So you have you attach a rubber band to a 1 kilogram block, and you use the rubber band to pull the block across a horizontal frictionless table. That means what you have here is, so if this is the block, right? So you're giving some kind of, a tension force, right? Pulling to the right, and there is a normal force, and there's a gravitational force. That means those three forces acting on it. Since it's only moving in the x direction, vertical forces technically cancel each other. But in a horizontal direction, you have just one force. There is no friction because it's a frictionless table, which means that either it's zero or it's very small, so we can ignore that. And then what happens here is this. If you're pulling with the rubber, you can see that if you started with object at rest, and then if you start pulling, it's going to start then moving. But it's not going to just move. It's going to start speeding up. Okay? It's going to start speeding up. And if you pull with a constant rate, then what you're going to give here, the object here is constant acceleration. That means the object is going to change its velocity at constant rate, which means, the acceleration, right? So you can see, right, when 1 kilogram block is pulled on a frictionless surface by a single elastic band stretched to its standard length, its acceleration, it accelerates with the constant acceleration a1. So if you do this, experiment and you get the data, you plot it, what you get here is this, which means acceleration is directly proportional to the force. So that's one of the important things that we're going to see, that the acceleration, it's actually, to the net force. It's a proportion to the net force, okay? Because if there are more than one forces, it's basically proportional to the net force. All right, so you can see, right, if you repeat this experiment, now by changing the mass of the object instead of the force, for example, so one of the things we're going to see here is if you start changing the mass of the object, going from, a 1 kilogram and 2 kilogram, 3 kilogram, 4 kilogram, while the same force is acting on it, what you will see here is then, well, acceleration is actually changes such a way that it decreases as a, as a function of, as a function of mass. Basically, that means, you change the mass, acceleration changes, and it changes such that acceleration is proportional to 1 of the mass. Okay, it means mass increasing decreases the acceleration, and that's the graph that we get. Well, conclusion here is then acceleration then is proportional to the force, which means the force is what makes object to accelerate in the first place. That means when we say that object is speeding up or slowing down, and they say, okay, that's because of the acceleration. Well, the acceleration is there because the object is being pulled or pushed. That is why it's speeding up or slowing down. So that's why if you have the box sitting there at rest, initially at rest, right? The only reason for it to start changing its motion is by pushing or pulling. That's why we have the rubber band, right? And you pull, as you pull, you exert force, and force basically makes the object then accelerate, which means it's going to then change its velocity. It's going to speed up. It's going to change its motion. Okay. And the equation is basically A equals force divided by mass, where the force is going to be in newtons after Isaac Newton, and it's going to be capital N, and the mass here has to be in kilograms. So That means, when, for example, 1 newtons of force acting on a 1 kilogram, block, right? Then acceleration will be 1 meter per second square. Okay. So generally this notation can be, or this equation can be rearranged. So it's F equals ma. And I imagine that's the second most famous physics equation after, of course, E equals mc squared. But F equals ma means that force equals mass times acceleration. Well, generally, what you have here is there's a net force and there's a vector acceleration. So you can think of like those are acceleration, and you can write it in terms of net, because that's probably a right way to represent it as a vector, because what we're saying here is that when there's a net force, there's acceleration in the direction of the net force. That means acceleration is proportional directly to the force in terms of its, the ratio of force over mass, and also it always has the same direction as the net force. Okay. All right, so now, one thing, if you remember, I mentioned that force of gravity is also known as weight. So approximate magnitude of some typical forces. So weight of a US quarter is 0.05 newtons. Weight of a 1 pound object is 5 newtons. Weight of a 110-pound person is 500 newtons. Well, because whenever you're talking about weight, well, weight is different from, for example, mass. Mass is not the same as weight, because mass is a scalar quantity, intrinsic property of the object, and it's measured in kilograms. Weight is actually a force of gravity on the object, and it's in newtons if it's in SI units, or pounds if it's in US or British units. So that's why this is kind of like the, what you see as equivalent. Weight of a 1 pound object is 5 newtons. That means 1 pound is equivalent to 5 newtons. That's a conversion factor going from, a pound to a newton. That's why if 110 pounds, it's, roughly 500 newtons, and so on and so forth. So you can say, right, proportion force of a car is about 5,000 newtons. Thrust force of a rocket motor is about 5 million newtons. Okay, so you don't need to know all of those things, except maybe like, let's say, conversion factor from pounds to the newtons. All right, so there are technically 2 types of masses. So there's a mass related to what we call, inertia. So object with twice the amount of matter accelerates only half as much as responds to the same force. For example, you have a box that is 5 kilograms and you apply force of, 10 newtons. Then acceleration equals force over mass. So 10 newtons over 5 kilograms, you get then 2 meters per second square. But then you replace the same, you replace the mass with a 10 kilogram object while still applying same force. So let's call this A1, F1, M1. So then A2 will be, force 2 over mass 2. Well, force 2 is still the same 10 newtons, but let's say mass now here is 10 kilograms, double the mass. Well, then what we get here is 1 meter per second square acceleration, right? That means the object with twice the amount of matter, which is twice the, amount of mass, will have only half as much, response to the same force. That means acceleration is half what it was before, because now the mass is, double the matter. So that means the more matter the object has, more it can resist accelerating, because mass is, you can think of like, let's say, it's object's way of resisting being pushed or pulled. So that's why heavy object is harder to push or pull, because they have too much mass, they can resist too much. Okay, so this is known as inertia. Okay, it means the tendency of an object to resist a change in velocity is called inertia. And the mass used in a equals F over m in equation, right, or F equals ma equation, is known as inertial mass. But there's, there's also, you're going to see there's also a gravitational mass, right? There's also a gravitational mass, which is basically comes from the gravity. And so let's say F of G is known as m times acceleration, right? See, this is gravitational force, which is, again, is mass times acceleration. But since it's a gravitational acceleration, it becomes mg. That means this mass is the gravitational force over g. This is known as a gravitational mass. So this is inertial mass, This is gravitational mass. And technically they are always, experimentally proving to be like about same value. Okay. So that means there was like, a lot of debate. Are they exactly the same thing or they're different things? So experimentally they're very close, but there's a little bit of differences actually, enough difference that, physicists were debating, are they the same or are they different? But mostly you can treat them as, either the same or having the same quantity. Okay, so here's then what I have. There are 3 laws of motion. Okay, so then we're going to look at in terms of Newton's laws of motions, 1, 2, and 3. So one of the things you can see here is, generally we kind of already talked about, this image, right? We talked about this picture over here when we said, okay, so there's a tension 1 and tension 2, and this box then will be technically, let's say, accelerating because of there's the non-zero F net, right? So that means, their effects here is, if you do a parallelogram, you can see this is the net effect. That means it's going to be then accelerating. Okay. That means, one of the things we have here is this. Newton's second law tells you what needs to be done in order to make the object accelerate. And what we need to do is to have a non-zero net force, such that forces don't cancel each other. That means F net must be non-zero. Well, F net is a vector. So there is a F net in the x direction, I hat, plus F net in a y direction, j hat. Well, at least one of them must be non-zero in order for F net not to be 0. That means what I have here is idea about, accelerating comes from the fact that you have to look at it in terms of your force. All the force components, x direction, y direction, z direction, and find something that is non-zero, then you can relate that to the acceleration of the system. Okay, because acceleration is F net divided by mass. So if F net is 0, then it's 0 divided by mass, acceleration is 0, which we'll see is actually the, Newton's first law of motion. But second law gives us condition for the acceleration. And we are talking about why then the system is accelerating. Because, for example, if you have an object of 5 kilograms, and let's say this object has 2 forces acting on it. For example, here's F1 with 20 newtons I hat. And let's say here's another force, F2, with, for example, 5 newtons, negative 5 newtons I hat. Well, then technically I have to make this as a, 1/4 of the distance, right? Like that, or the length, because, it's a vector. So the length of the, force has to be proportional to its magnitude. Then if I'm looking at the net force, or, let's say F net in x direction. So this will be then F1 I hat, plus, let's say, in terms of like plus F2 I hat, right? But I can see then technically this is then minus 2, F2 I hat. So this is then 20 newtons I hat minus 5 newtons I hat. Because both of them are I hat, I can add them together. So I get 15 newtons I hat. Means that the net force here is in a I hat direction. So it's 15 newtons in a positive I hat direction. Then what is the acceleration? Well, it's then F net divided by mass. Well, it's 15 newtons I hat divided by 5 kilograms. Then you get 3 meters per second square I hat. So you can see, right, it has the same direction as the force, right? But its magnitude is the force over the mass, F net over the mass. And that's what you have. That means in order to find acceleration, you need to first find the net force, if there are multiple forces, and then divide that by the mass of the object, then you have your acceleration. And then once you have acceleration, then you can use that in kinematics. Because let's say if this force is constant, that means it doesn't change as a function of time or as a function of position, then if you have this acceleration and your object started from rest, you can find what is the velocity after, let's say, 1 second or 2 seconds or 3 seconds, right? Because if this is 0, then it's 3 times 1, 3 times 2, 3 times 3, and so on and so forth. That means you can see how it changes its velocity as a function of time. All right, so let's look at this example over here. So you have a friend that has given you a special gift, a box of mass 10 kilogram with a mystery surprise inside. The box is resting on the smooth, smooth, which smooth by the way means frictionless, horizontal surface of a table. So we want to determine the weight of the box and the normal force exerted on it by the table. All right, so then one thing we can do here is this. All right, so I have to do that, so give myself some room. So things like this, then I'm gonna take the box and put it at the coordinate system, center of my coordinate system, then draw, forces that I have acting on it. So I have gravity, right? I have gravity straight down, and I have normal force straight up. In this case, because it's perpendicular to the surface. All right, so then what I have here is then, forces, the net force in the x direction is equals to 0 because there are no forces in the x direction. Then forces in the y direction then equals to the normal force minus then the gravitational force, because we take up to be positive, right? So then normal force is positive and then gravitational force is negative. All right, so now what I have here is the box is sitting, at rest. That means F net then technically 0 because the system is not accelerating. Okay. Now what it means then, the normal force then is equals to F of G, which is equal to the gravitational force. Now, what is the gravitational force? Well, gravitational force equals m times g. So the mass of 10 kilograms times 9.8 meter per second square. So then F of g is equals to 98 newtons, which means then normal force is also equals to 98 newtons because it's equal to the gravitational force. That means we found the weight and the normal force exerted by the table. So that's part A. Now, next what we have is this. It says, now your friend pushes down on the box with a force of 40 Newton. Again, determine the normal force exerted on the box by the table. Well, didn't we find the normal force right now to be 98 Newtons? Well, it was 98 Newtons when it was only those two forces acting on it, on the object. But we're going to see that if there are other vertical forces, the normal force is technically a adjustable variable force, so it can actually change its value. Gravitational force is fixed because it's mass times 9.8. Mass is 10 kilogram, doesn't change. 9.8 doesn't change, so gravitational force is still the same. But normal force can actually adjust itself. All right, so then let's do this. So I'm again going to do the free body diagram. So here's a free body diagram. I take my object, put it at the center, and I drew all the forces. What I have now is still gravitational force straight down, normal force straight up, but now I also somebody pushing down. That means I have this force over here, so some applied force. When you start getting more forces acting on the object, it's best to write down a table, the one that we use for the vectors. So now we can call this forces, then x component and y components of the forces. And then write down that, okay, so I have F of G, I have normal force, and I have applied force. Because organizing allows you to get a little bit better, or minimize the, the mistakes. Remember, so technically adding all those forces gives you F net, but the idea here is this. So in x direction, you have no forces acting in x direction, so your F net has no x component. But then you have all those three acting in a y direction. So then you look at, okay, F of G. Here's then F of G, and then since it's acting down, so put it negative. Then normal force, you put the normal force here, normal force acting upward, so it's positive. Then applied force. Well, applied force only in the vertical direction, but it's down, so it's negative. But the box, think like this, if you're pushing the box still not accelerating, that means net force is still 0. So then you say, all right, so then F net in a y direction is equals to negative F of G plus normal force minus F of A equals 0. Now, what is the normal force? Well, it's equals to F of A plus F of G. Well, F of A we're given as 40 newtons, and F of G we calculated as 98 newtons. That means now normal force, you can see, right, it's increased to 98, right? So 138 newtons. Why? Because normal force is what prevents object from accelerating down, because now there are two forces pushing it down. Normal force has to prevent. So then it's actually increases the value to cancel not only gravitational force, but also applied force. Right? So that's why it's actually increased its value. Part C. Now, if your friend pulls upward on the box with a force of 40 newtons, now what is the normal force? Well, what I'm going to do, I'm going to then come back to the same thing that I did for part B. I'm going to change then my diagram, because now diagram has a force acting upward. So applied force, right? That means in this case, when I go to the applied force, I can say, all right, it's positive now. It's positive. So then my equation becomes negative f of g plus normal force, then plus f of a, because both of them upward, equals 0. Then normal force here then end up being the difference between f of a, or like, let's say f of g and f of a, like this. So which will be then 98 newtons minus 40 newtons. So then the force of normal, the normal force right now will be difference of those two. So in this case, it will be 58 newtons. So you can see, right? The normal force is 98 or 138 or 58, well, depending on other vertical forces. Because here, normal force in part A, normal force alone has to balance the gravitational force. So it can adjust itself to be 98. In part B, normal force had to adjust itself to be equal to the gravity and applied force, which are both down. But in part C, normal force has a help, because there is an applied force upward with 40 newtons. That means then the combined upward forces should be equal to the downward force in order for the object to still remain at rest. Okay. Let's look at another example here. We have what happens when the person pulls upward on the box in the previous example with the force greater than the box's weight, say 100 newtons. Well, this is 98, this is 100. That means the guy, or person can actually start lifting the box, which means, our box is now being lifted, and as it starts lifting, moving upward, right? It doesn't make any contact with the, with the surface anymore. That means the forces, by the way, this is how I also sometimes write net force, some of the forces. So this will be then, applied force, upward, minus gravitational force. But now what I have is this. There is an acceleration. Why? Because the forces are 100 minus 98, so they're not going to cancel each other. So then this is equal to the mass times acceleration according to the Newton's second law. That means Newton's second law tells you that if your forces in one specific direction don't cancel all each other, then their sum, or their difference, right, is equal to the mass times acceleration. That means there will be an acceleration if the forces, are imbalanced. All right, so what we get here is we get 2 newtons equals mass times acceleration. Then acceleration equals 2 newtons divided by mass. Remember, the mass was 10 kilograms. That means we end up with 0.2 meter per second square j-head direction. So there will be an upward acceleration, because technically there was a j-head direction force. That means acceleration will also be in a j-head direction. All right. Now let's look at Newton's first law. So we're kind of going back a little bit, but first law, sometimes it's easier to go to the second law and then come back to the first law, because first law basically tells you what happens when the object has all the forces acting on it cancel each other. Okay, so that's what the Newton's first law tells you. That an object that is at rest will remain at rest, or an object that is moving will continue to move in a straight line with constant velocity, if and only if the net force acting on the object is 0. Right, so we know what happens when the net force is not 0. Object accelerates. But now it says if the object has the net force equal to 0, then if the object is at rest, it's going to remain at rest. And if it's moving with constant velocity, it's going to continue moving at constant velocity because of that, net force equal zero. So that's why the Newton's first law is known as law of inertia. Actually, the Galileo who came up with this, with this hypothesis, he just, the Isaac Newton kind of took that and put it in a, much better explanation of that, and in a much greater, let's say, concept of force, right? So, and we basically call this Newton's first law rather than Galileo's. But Isaac Newton actually, gave credit, to all of the, let's say, not a scientist, because we didn't call them scientists, but natural philosophers that came before him. And he did say that he's standing on the shoulders of giants. And those giants basically were Galileo and Kepler and Copernicus. Okay. And you guys should know all of those names. So Galileo, Kepler, Copernicus, right? Those are, let's say in terms of physics and astronomy, those are basically the giants. All right. So the Newton's first law is a law of inertia. If an object is at rest, it has a tendency to stay at rest. If it is moving, it has a tendency to continue moving with the same velocity. You actually experience this every day. You get into your car, turn on the ignition, then, press the accelerator in your car. And what happens? The car is moving forward, but your body is not, because it doesn't have an engine. So your body kind of moves backward. It's being pushed by your seat, right? So every time you speed up, your body kind of moves backwards. Why? Because your body was at rest, and it wants to stay at rest. You have to actually push it with your car. And then when finally your body gets used to the, being moving, so imagine you're moving in your car and then you hit the brake. Well, when you hit the brake, your body doesn't have a brake. Your body wants to continue, move forward. So that's why, if you hit the brake and you don't have a seatbelt, your body going to continue moving, you're going to, hit the steering wheel, or maybe like, let's say, even worse, right? But your body will want to continue moving because of this, right? If it's moving, it has a tendency to continue moving with the same velocity. You hit the brakes, so your car is slowing down, but your body doesn't have a brake, so it wants to continue moving. So that's why you need a seatbelt to, slow down your body as well. All right, so technically then, Newton's second law describes non-uniform motion when objects speeding up or slowing down or changing direction. Newton's first law then describes uniform motion, because uniform motion means constant velocity. Well, technically, even if you're at rest, it's still a constant velocity, because if you continue being at rest, your velocity is constantly zero. Well, it is constant. So then what we do here, we have a different name for that. We call it mechanical equilibrium. That means if object here is at rest, or if object moving at constant velocity, that's because the forces cancel each other. What is the result, or what is the consequence? Well, there is no acceleration. That means if the net force is zero and it equals to mass times acceleration, means acceleration is also zero. That means equilibrium means no acceleration. But you have those two scenarios, right? Where you can be at rest and not accelerating. We call that static equilibrium. Or you could be moving at constant velocity and not accelerating, and we call that dynamic equilibrium. That means there are two kind of like cases for the equilibrium. One, when you're moving, constant velocity, straight line. One, when you're at rest, and not, changing your motion. All right, so this is basically what I was kind of talking about. If a car stops suddenly, you may be thrown forward, and you not have forward acceleration relative to the car. However, there is no force pushing you forward, so that's because of your body's tendency to move forward, even though your car basically slows down and stops. Okay. So generally what we do here, we use what we call inertial frame of reference or inertial reference frames. Those are basically either your car or your room or your house or your planet, where when you do an experiment and whatever, let's say, experiment you're doing, it obeys Newton's laws of motion. So any type of, frame of reference, again, frame of reference can be your house, your room, a car, plane, bus, if you're doing an experiment and Newton's laws are obeyed, then you can call that inertial reference frame. And generally those are the frames where, your frame can be at rest or your frame can be moving, but such that it's moving at constant velocity. It means it's in equilibrium. So, which means acceleration is zero and there is no net force. For example, think like this. You have an airplane that is not accelerating. That means it's just moving at constant velocity, straight line. You put a ball next to you and it stays in place. But as soon as the, let's say plane starts speeding up or slowing down, then you will see that balls are rolling backward or upward, right? Depending if it's speeding up or slowing down. Well, that's because, and again, nobody's pushing or pulling the ball. So then why is it accelerating backward or forward? Well, because this frame is not an inertial reference frame. So then accelerating reference frames are not inertial reference frames. That means we're going to assume that all the frames are going to be inertial reference frames. So then for us, it's easy to work with them and be able to, expect all the laws of motion, all the Isaac Newton's laws of motion to be obeyed. Okay. So Newton's third law is kind of a unique in a way that is a little bit different. So what it does, it describes what happens when two objects interacting rather than what happens to one object when force is acting on it. So then Newton's third law basically describes what we call equilibrium. Sorry, Newton's third law describes, action-reaction forces. It says that for every action, there is opposite but equal reaction. Okay. So then when you have a force acting on the object, then that object basically exerts force on the agent itself, right? So you can say, right, forces exist at the point of contact between agent and the object, okay? And forces exist due to interaction happening now and not due to what happening in the past. Consider flying arrow. Pushing force was required to accelerate the arrow as it was shot. However, no force needed to keep the arrow moving, forward as it flies. Okay. It continues to move because of inertia. Also, you can think of like, let's say there's a good way of understanding this action reaction is when you push something, that something then pushes back. For example, if you shoot a rifle, then you have interaction between rifle and the bullet. So the rifle pushes the bullet out, but the bullet also pushes the rifle in the opposite direction, and the rifle basically does a little bit of recoil, right? So it goes backward a little bit because if you push the bullet in the forward direction, bullet pushes rifle in the opposite direction. So this is basically those action reaction, forces. For every action, there's opposite and equal reaction. All right, so again, this is again a tactic to do the free body diagram, identify all forces acting on the object. I can explain that, right? So do a coordinate system, put the object at the center, and then draw all the forces as vectors with the direction, and then correct, let's say, labeling, right? So you have to use the notation, correct notation to indicate what type of force we have. Okay, and then you can, describe if there's a net force which is equals to 0 or not 0, because if the net force is not 0, then you have an acceleration. Right, so here's one simple example. You have a car is being towed to the right at the constant speed, which is the correct free body diagram. Now you take the car at the center of your coordinate system, and you start drawing, your forces. Well, there's a stream, there's a rope to the right, so there's a force like that, which is the tension. Well, there is the surface force, normal force upward, and there's a gravity downward. Okay. So the question is, are those the only forces acting on it? Well, it would have been if the car was speeding up to the right, but we know that it's being towed at constant speed. That means net force should be 0, which means in X direction, right, should be 0, and in a Y direction should be 0. Which means then in the X direction should be another force that cancels the tension, and that's obviously, kinetic friction, as we learned. There you go. So another one, a car is parked on a hill. Draw the correct free body diagram. Again, what we have here is you have a car that is parked, so we draw the coordinate system like this, right? So such that car is at the center. Now we have the gravity acting on it like this, and there's a normal force acting like that. But the car here is at, in equilibrium. Why? Because it's parked. So it's a static equilibrium. Previous one was a dynamic equilibrium. That means, again, there has to be some kind of force in the opposite direction of the gravity, because gravity, then technically you can say that it will have, a components. So it will have components where there is a gravitational force in the y direction, gravitational force in the x direction. Those two cancel in the x direction, these two cancel in the y direction. You can write that. You have three forces acting on the object to keep it at rest. All right, so that's it for this chapter.